Unit 10b will continue our conversation about oscillations. Another example of a simple harmonic oscillator is a simple pendulum, which has a mass suspended from a thin massless string. This pendulum will exhibit oscillatory motion because it moves back and forth between 2 points repetitively, and therefore it will have a frequency and a period. It will also have an amplitude, and for a pendulum, since we're moving in both x and y, the amplitude is reported as the angle theta. The amount of angular displacement that we undergo will describe the amplitude of a simple pendulum. And if we wanted to solve for the period of a simple pendulum, we can do it using this equation, which only involves the length of the string and the gravitational field that the pendulum is present in. The mass has no effect on the period of a pendulum. So here we see an example of a simple pendulum. The oscillation will start as it passes that midpoint. We see that it moves to the right, past the midpoint one more time, and then back to the left. And this oscillation takes place over about 2 seconds. That's our period for that oscillation. This is for a string that is 1 meter long with a mass of 1 kilogram and an initial amplitude of 15 degrees, as you can see shown on this protractor. You'll notice that the energy changes between kinetic energy and gravitational energy throughout this motion. As the object raises up in height when it goes to the right and the left, it will have gravitational energy, and as it passes through the midpoint, it will have all kinetic energy. And now, since we're talking about angles, there is a very useful term called the angular frequency, which describes the amount of radians that our oscillation undergoes in a given amount of time. So this is a lot like the frequency, except we just multiply the frequency by 2 pi, so that now, instead of having units of per second in the frequency, our angular frequency will have units of radians per second. So every time we undergo one cycle, it's like we are undergoing 2 pi radians throughout that oscillation, or 360 degrees around the unit circle. Every time you complete one cycle, you've completed 2 pi radians. And we noted for the simple pendulum that it changes its energy from gravitational to kinetic energy. And that is a very similar case to the spring mass system, which changes between spring energy and kinetic energy. When this spring is all the way to the right at its maximum displacement from equilibrium, it has no speed and the spring is stretched out. So it has all spring energy and no kinetic energy. Then, as the spring passes the midpoint, the equilibrium point, the spring is no longer stretched, but the mass is moving with a velocity, so we gave up all of our spring energy into the form of kinetic energy. And if we set up energy conservation for this situation, we can solve for the maximum velocity that that spring mass will have at its equilibrium point, and that maximum velocity is just based on the spring constant, the mass of the object, and the amplitude of the oscillation. You'll see that we have a term that looks a lot like the period of a spring mass oscillator, and really that is the angular frequency. If you work out the variables here, you will see that the maximum velocity of this oscillator system is based on the angular frequency times its amplitude. Another example of a simple harmonic oscillator is uniform circular motion. So imagine the needle on a record player moving in a circle along that record. We can model the horizontal and vertical positions of an object moving in uniform circular motion by using a cosine and a sine function as we travel around the unit circle. So if you know the amplitude and the period of your oscillation, you can predict what position we will be at any time. And for this oscillator, the maximum displacement that you will get from equilibrium is the radius of this circle. So in the case of uniform circular motion, the amplitude of the oscillation is the radius of that circular motion. Damping is a process that removes energy every time that this oscillator goes through one cycle. So you'll see in the case of this pendulum down here that it looks a little different than the last example. We start our oscillation and it begins oscillating, but it loses energy. It gives up some of that energy in the form of thermal energy because we now have air drag or friction or internal friction within this spring itself. And those mechanisms will give up energy in this oscillator in the form of thermal energy, and we can never get that energy back. Same with the spring mass system. The spring mass system in an ideal case would oscillate forever, but in a damped case, it loses some of that energy, eventually slowing down and coming to equilibrium at the equilibrium point. And it's important to note that damping will only affect the amplitude of the oscillation. It will not actually affect the period or frequency of these oscillations. So here you can see an example where we have an undamped simple harmonic oscillator. It has an amplitude of 0.5 meters and a period of 2 seconds. And this looks just like our standard cosine wave graph that we've seen for other oscillators. But if we have damping included, we have to include this damping term in our wave equation. This damping term tells you the percentage of amplitude kept every cycle. So if we keep 90% of our amplitude and we lose 10% every cycle, you would plug 0.9 in for this capital K. And it's just raised to the power of our current time over the period. So this graph down here will show you the example of what happens when we include that damping term in our calculations of the displacement of a simple harmonic oscillator. It loses 90% of its amplitude every cycle. So it goes from 0.5 meters for its amplitude to 0.45. And this is an exponential decay function. So the amplitude of the previous cycle will be what modifies the amplitude of the current cycle. It's not like we just lose 0.05 meters every cycle. That amount will change based on what the amplitude was in the previous cycle. That'll cover everything for Unit 10B. I'll see you in the next one.